solar cells to LEDs. So this is a very important lecture, and it's not just a guest lecture because you're going to be examined on the content that we'll cover today. So over to Professor Abdi.
Thank you, Zabi. Okay, Dr. Zabi has given me a next to impossible task of covering in 70 minutes, although it'll probably take more like 90, the p-n junction. And I will describe this to you in very conceptual terms. You may not be accustomed to that because this requires 90% thinking and 10% analysis. You may be trained to do it the other way around. So it's very important that you look at the concepts and you dwell upon them at length. For 1 hour of lecture, typically, to get all the content, it's 8 hours of work on your own. So please be prepared for that. If you understand the p-n junction at this level, your electronics courses will be a lot easier, and you'll have a good fundamental grasp to serve you if you stay in the electronics area. Okay, a couple of rules. No talking while I'm speaking. No discussion until I finish. If you wish to ask questions, just raise your hand. I will ask questions as well. Don't be afraid to give wrong answers, because most people share common misconceptions. And so if it is wrong, I will point out the correct reasoning, and everybody benefits. Okay, so I will ask questions occasionally to test things. Now what happened here?
It goes up by itself.
All right, so we'll leave that one alone. You have seen energy band diagrams, and it's sort of the modern approach to thinking of semiconductors, insulators, conductors, and so on. One can look at these p-n junctions and all transistors purely in terms of energy levels and Boltzmann statistics and so on, but the inventor of the transistor, William Shockley, recognized that for most people these are very abstract notions, and that it would only be possible to use these devices if they could be understood in classical ways, using particles and things that are very familiar to us, rather than wave functions and energy levels and so on. So I will give you a particle-based approach to the p-n junction, because at your level of learning that is the appropriate approach. Then if there is need, you can go to more abstract ways which are in some ways more correct later on. Let me give you a list of the concepts I will cover. We'll start with that. Underlying the entire p-n junction, and in fact all semiconductor electronics, is something that is taken from gas laws and thermodynamics. It's a profound relationship called Boltzmann processes or Boltzmann statistics. And I will illustrate this with a simple example in a moment. If I can hear you, you are violating the rules. No talking, please, while I'm speaking. Then we'll talk about recombination generation, which is unique to semiconductors. Because only in semiconductors do you have two independent, oppositely charged mobile carriers or mobile particles. You do not have them in metals, and you have no mobile charges at all in insulators. Only in semiconductors do you have things which are equal and oppositely charged. So there's this special process that kicks in. Then we'll talk about diffusion and drift currents. And I will invoke, it's not really a new concept, but I'll invoke things that you have seen before, but they'll be really put to test in terms of your understanding here, and they are charge neutrality and Kirchhoff's current law. All right, let's start with Boltzmann statistics. All microscopic processes are subject to thermal actuation and random motion because of energy received from the sun, ultimately. So if one has, for example, this is the surface of the Earth, and one has a big cylinder here which is closed, and inside this there's a gas, and this is the height from the Earth at a certain particular point here. The density of gas particles here at this point, n of h, is proportional to the exponential of minus u over kT, where k is Boltzmann constant, T is absolute temperature, and u is the potential energy at that height for a particle of mass m. What this says is that the higher you get up there, which requires a larger u, you get an exponentially lower number of particles. Now, it's all worth thinking about. You've studied this stuff. When you have gravity, everything is attracted towards the center of the Earth. We are. That's why we're grounded. But why are gas particles detached from the Earth? If they're up there, they're detached. They're floating. We don't float. They do. Why is that? Why is that? You've all taken thermodynamics. Yeah.
So the kinetic energy due to the collision is greater than the potential energy attracted by the Earth.
Kinetic energy due to collisions.
The random motion.
Which is due to what?
The random motion.
Due to what? What's that?
Kinetic energy, and they're able to overcome the gravitational force.
Due to what?
The kinetic energy gains from the room temperature.
Thermal energy. Due to thermal energy. So thermal energy is received from the sun always. Everything starts from the sun. Okay, if the sun was not there, we wouldn't be here. So it's received from the sun, that actuates these particles, vibrates because they absorb energy, and that energy can be sufficient to overcome the pull of gravity. Now this is a statistical process, because not only do you absorb energy, but these particles collide with each other. And so there's a whole scrambling, like hundreds of billiard balls on a table. They all collide with each other all the time. The net effect is that you can talk about things only in averages, not for individual particles. And this is the distribution function on average for the density of particles. Now once you understand this, you can understand why our atmosphere is the way it is. Our atmosphere starts off being most dense at the Earth's surface and slowly gets less dense, following precisely Boltzmann statistics. You also understand why it gets colder. At 30,000 feet, what roughly is the temperature? Anyone of you who's traveled on an aeroplane with a display should be able to say that. Tell me that. What is it? 30,000 feet, what's the temperature outside? It's about minus 20 degrees centigrade. Why is it minus 20? What sets that? Test of thermodynamics.
There are less particles.
It's a density of particles. Temperature is related to the density of particles. Although each particle has on average the same energy. Each particle has on average the same energy. What is that average energy? At a temperature T, what is that average energy? 3/2 kT. There are 3 degrees of freedom. 3/2 kT. 3 degrees of freedom. 3 orthogonal directions in which it can move. They all have the same energy, and yet as they get less dense, the temperature goes down. And that's actually the fourth law of thermodynamics, which relates temperature to density, and the two are very interdependent. So you have rare numbers or fewer particles, lower temperature. All of this comes out from this. And it's also, again, a test of your understanding of thermodynamics. You should have this stuff at your fingertips. You spend a whole semester learning that. You haven't taken that yet? Okay, so this is what you're answering. What's that?
A-level concept.
A-level concept. Okay, good. All right, good. That's encouraging. All right. Now, when we apply this to semiconductors, you've looked at these energy levels. You've seen how solids are made. So you have these bands of allowable energy. We draw it in this fashion. Bands of allowable energy, where you have, let's say, a band here which is full of a dense, it's not an infinite number, it's a very large, discrete, countable number of possible occupiable energy levels. You have another band here of possible occupiable energy levels, and because of the way the solid forms and coalesces, there forms an energy gap of forbidden energies that cannot be occupied. In semiconductors, these energy levels, simply because they're countable and discrete, can account for every possible atom that there is. So that these energy levels here are completely populated, and these energy levels here at 0 Kelvin would be completely empty. Then there is an energy gap here, and what makes a semiconductor different from an insulator is that the energy gap is modest in amount. In the case of silicon, which is the most common semiconductor, this energy gap is 1.1 electron volts at 0 Kelvin and 1.2 at room temperature. So we have an energy gap here. Now, since the electrons associated with the atoms there are, these are, by the way, electron energy levels. I said that each atom accounts for it, but atoms have electrons, and so the electrons in the atoms occupy these energy levels down here. We're plotting electron energy going up. At room temperature, these will acquire additional energy. At 0 K, they have only energies endowed by the Pauli exclusion principle, which forces them to slot into these levels and remain there. However, at room temperature, they acquire additional energy. We've talked about it, 3/2 kT, for example, and that can cause, because of a distribution like this, can cause them to surmount this gap. And therefore, you will have some number of electrons that sit up here. And what is interesting is that if this is completely full, it's like a packed bus or a packed garage. There's no room for the cars to move. They're jam-packed completely. But if an electron makes its way through there because of thermal energy, it has lots of vacant energy levels. So that means that if it receives additional energy, it can move to a higher energy level. If it receives an electric field, it can accelerate, which requires higher energy, and there's an energy level present there. So this is like a garage which is packed full of cars where nothing can move. Now, if this is a multi-story garage and the second level happens to be empty, and if a car moves to the second level, it can move around freely. And that's the analogy you should keep in mind. So, thermal energy actuates electrons to here following the Boltzmann process. Now, this process of thermal energy actuating electrons to there is called thermal generation. And we talk about thermal generation in the following way. The word generation needs clarification here. Thermal generation means that electrons that couldn't move because there was no space for them to occupy additional energies suddenly become mobile if they appear there. So we are generating mobile carriers that can carry currents. because ultimately it's those currents we will use when we employ this as a device. So the word generation means generation of mobile carriers. And this is an ongoing process because continuously photons from the sun are being absorbed by the sample. So, thermal generation of mobile carriers, this process is proportional to, by Boltzmann statistics, exponential of the energy that they must overcome in order to become mobile. And that's minus Eg over kT. Now when these electrons move up there, they leave behind vacancies, which I presume you have learnt are mobile themselves, in the sense that it's actually only electrons that do the moving, but they can move around between vacancies, and those vacancies appear as if they're positively charged mobile particles. This only happens in a semiconductor. Therefore, do not make the mistake that some people do, which is to say that, and you'll be surprised how easy it is to make. If you have a capacitor, for example, and you charge it, do not think that those are holes and these are electrons. There is no such thing as a hole in a metal, and a capacitor is nothing more than a metal plates. What you have in positive charge here are the atoms which contributed these electrons. And since they gave up an electron that moved to the other plate, you've got a net positive proton that contributes a positive charge. But in semiconductors, you have mobile positive charges and mobile negative charges which are independent of each other. They have to obey charge neutrality, but they're independent. Okay, now, we create electrons at the same time we create holes. Let us call the number of mobile electrons n per cubic centimeter. Since we're counting particles, it's just a number, but it's a volume density per cubic centimeter. And number of mobile holes we'll call P per cubic centimeter. Now when you have mobile electrons and holes swarming around each other, think of them as independent particles. It is quite reasonable to think that they will attract each other, but please remember that the hole is not a positively charged particle. A hole is nothing other than a vacancy into which electrons drop. So when we say that a hole and an electron attract each other, all it means is that an electron is attracted into a vacancy, into which it will come and sit, and complete a covalent bond that had been disrupted to begin with. So this process is called recombination. Electrons and holes recombine, or in each other's vicinity. We call it that they annihilate each other, which more precisely means that electron drops into a vacancy and becomes immobile. That's all it means. That's called recombination. And then, because of thermal energy, the same electron may be torn away again and become mobile again. And the moment it's torn away, it leaves behind a hole. Now, in an intrinsic semiconductor, intrinsic means a pure semiconductor, from the reasons that I've just given you, the number of electrons is going to be equal to the number of holes, because every electron that jumps the gap leaves behind a hole. So the numbers are equal. And we give them a particular notation n sub I, number of electrons or holes in an intrinsic semiconductor. The recombination rate always depends upon, is proportional to the number of electrons in a per cubic centimeter multiplied by the number of holes. Why is that? Because a recombination event requires two things to happen: an electron to be present in a certain place and a hole to be nearby for the electron to jump into. So if you have a deficiency of holes, the electrons cannot recombine. If you have a deficiency of electrons, the holes cannot recombine. You need both at the same place. It's a joint probability. Yes?
So in intrinsic semiconductor we are saying that n is equal to p, so why can't you take just one n or p, because the other would be sufficient to counteract that. For example, if we say it is directly proportional to n, that directly means that there are same number of p's also over there.
Okay, that seemed like a notational question. I've already answered that by saying n is equal to p, and we give it a number ni, and ni is not electrons, it's number. So it's an intrinsic number that applies equally to electrons and holes. So the important thing is the recombination rate. It's very important to understand that. Yeah?
Maybe explain how vacancies become immobile. You said that earlier they are mobile.
Vacancies are not mobile. Vacancies cannot be mobile, or they are, but only in a virtual way. Let's look at a classical model of a lattice. You have covalent bonds that hold the solid together. Okay? These are meant to be the nuclei, all put together in a crystal lattice. These are electrons that are shared between them to hold things together. Due to thermal energy, these, let us say one of these electrons can be torn out of the covalent bond. The covalent bond has an attractive energy. If thermal energy is strong enough, it can tear away this so that the electron becomes mobile. This used to be an electron here. That means that there's a vacancy left here. Now that vacancy cannot per se move. All that can happen is that, let us say, this electron could jump into that vacancy. If it does that, it will complete this bond, but it will leave behind an empty bond there. So we can think of electrons occupying nearby vacancies simply because of probability. They're electron waves, you see. They're probability clouds. So that electron is actually, strictly speaking, not localized, and it can end up filling this, leaving a vacancy there. Then a nearby electron here could fill this vacancy. And so what we see is the vacancy is virtually traveling, but it's actually the electron that's doing the work. It looks like a positive particle. Okay. So, the recombination rate always, fundamentally, depends upon the product of the number of carriers. That's very important. It's the probability of an electron and hole coming together in each other's vicinity. So it's a product of the probability of the electron and of the hole, because they're independent particles, statistically independent. Okay, that being so, here's what we can say. That in the intrinsic semiconductor, at equilibrium, it must be true by definition of equilibrium that the generation rate is equal to the recombination rate. Otherwise, the number of electrons would keep on rising indefinitely. Or if recombination was prevalent, it would keep on dropping indefinitely. So equilibrium means everything is equilibrated. Things are not changing over time on average. That being so, we've got expressions for thermal generation, we've got expression for recombination rate, and so we can say that in an intrinsic semiconductor, The recombination rate Ni squared, it's proportional to Ni squared, is itself proportional to the exponential of minus Eg over kT, which is the generation rate. Proportional because there's some constants involved which I haven't put in there. So that implies that Ni is proportional to Eg over 2 kT. In silicon, at room temperature, because of this relationship, we can say that Ni is equal to a particular number, 1.5 times 10 to the 10 per cubic centimeter. That's in silicon. And if you change the temperature, that will change because there's an exponential dependence there. You can see that if the temperature here changes, this must change to accommodate, to make the equality. Now you've seen extrinsic semiconductors because you've seen what doping is. Extrinsic semiconductors contain dopants. You can have donors which give extra electrons, or you can have acceptors which give extra holes. Donors or acceptors. We give a certain density to these. Donor density is N sub d per cubic centimeter. This is the number of impurity atoms that we'd be putting in. In the case of silicon, this would be drawn from column 5 of the periodic table. Acceptors, column 3 of the periodic table. Now this is totally under human control. You can determine how many of these dopants enter your sample. There's a particular materials process by which you introduce these things. They go and occupy, displace silicon atoms, occupy the sites and either yield an extra electron for which there is no need. So in this picture here, if you put a donor in there, it has 5 electrons in its outermost shell. 4 are enough to complete the covalent bonds. The 5th has no job to do, so it just wanders off. You understand? That's all there is to it. Each one of these will contribute a mobile electron essentially for free, with almost no energy. Similarly, this will contribute a mobile hole. Now this imbalances the process here in the following way. Now, the recombination rate is proportional, as always, to P times N. And in the case, for example, of donor impurities, each one gives a free electron. And if these donors happen to be much bigger than 1.5 times 10 to the 10, then the total number of electrons is dominated by that. Supposing this is 1,000 times larger. Supposing this is 10 to the 15, this one here. 10 to the 15 due to that, plus 10 to the 10 already here, is still 10 to the 15. Correct? So, since these tend to be much bigger than that, what we would find is that we would have, for the number of electrons, the dopant concentration and some new number of holes, and we will give it a subscript n here to indicate that these are holes sitting in an n-type doped extrinsic semiconductor. Or if we had this type of dopant, we would have Na times a new number Np of holes. So introducing dopants is going to affect this product in some way. But in equilibrium, it must match generation. Otherwise, you'd have a continuously increasing or decreasing number of electrons or holes. The generation rate is not affected by dopants as long as the doping density is modest. The generation rate only depends on temperature. but generation only depends on temperature. Therefore, at equilibrium, Pn times Nd must still remain proportional to the generation rate, or rather, since I haven't put a constant here, it is a proportionality, but when you put the constant equals the generation rate, that generation rate is unchanged, and it's unchanged compared to the intrinsic case. It's always unchanged, always the same. Only depends on temperature, is not affected by doping. Well, we know that in the case of the intrinsic semiconductor, the balance leads to that proportionality over there. Now we're going to have the same proportionality appearing here, because the generation rate is unchanged. And since the constants of proportionality are the same in all cases, this implies that Pn times Nd, I'm referring now to that equation, must be equal to Ni squared. In other words, I eliminate all the constant proportionality by balancing the product of two carrier concentrations with another product of two carrier concentrations, thus getting rid of all the proportionality constants, because I'm now comparing apples and apples. And equivalently, Na times Np is also equal to Ni squared. And notice Ni squared is given. 1.5, I know exactly what it is. Now what does this mean? This is a logarithmic scale. This is a vertical ruler, log scale. And I will put this Ni here, and I'll say N is equal to P is equal to Ni, and this is equal to 1.5 times 10 to the minus 10. Again, this is not God-given. It's for silicon at room temperature. But since that's the most common condition, we just use that number. Now let me compare this on the same log scale. Log means you go up in decades, with a doped semiconductor. So this would be for intrinsic, and this would be for extrinsic or doped. Let's take the example of a practical doping level. A light doping level would be 10 to the 15 per cubic centimeter. Does anyone remember how many silicon atoms there are per cubic centimeter in a solid? 10 to the 22. So when we dope at 10 to the 15, we are introducing one dopant per 10 million silicon atoms. Tiny amount of doping as far as the silicon goes. Huge amount of doping as far as this number goes. Very important for you to get a sense of magnitudes. The doping does not destroy the silicon. There's only one dopant on average per 10 million atoms. But it swamps out this number. So on a log scale, the dopant might be up here. Let's say 10 to the 15. What this relationship tells us is that the corresponding Pn is going to be such that this times that must be equal to this times itself. So on the order of magnitude, this is 10 to the 20. If that's 10 to the 15, this is on the order of 10 to the 5. Now look at this case. This is a practical light doping. You can have heavier dopings all the way up to 10 to the 18. Look at this. These are 10 orders of magnitude apart. That's 10 billion numbers apart. So when you look at, let us say, mobile particles moving due to an electric field, you're going to have a tiny number of holes and a huge number of electrons. These are called minority carriers. These are called majority carriers. And the interesting thing is, you might think that since they're so tiny, we can neglect them, but they actually determine everything that goes on in a PN junction. So I'm alerting you to their importance now. So these are called minority carriers. And these are called majority carriers. charge carriers. Now let's look at the concept of diffusion currents. You're all familiar with the experience that if someone is wearing a strong perfume in the room, eventually you can smell it. That is an example of diffusion. The perfume molecules spread throughout the room because of collisions with air molecules. And what drives them is the second law of thermodynamics, which seeks the most probable condition for the molecules, which in the case of a room would be a uniform distribution throughout the enclosed walls. So what we have is, due to a purely random process of agitated air molecules, the diffusion of a particular type of molecule that is newly introduced into a steady state environment. In other words, to quantify this mathematically, what we say is that if there is a concentration gradient, then the second law of thermodynamics causes that gradient to slowly relax to zero. So if there's a strong amount of perfume here and nowhere else, there's a concentration gradient. If you plot the concentration peak here and then quickly goes down to zero. So if we look at that from this perspective, if we have a number of something as a function of distance in one dimension, let's say this is a number of some quantity. I'll use y here because I don't want to imply electrons or holes for now. And if there is a concentration gradient of some sort, let us say the concentration gradient is like that, it doesn't have to be uniform. Then by the second law of thermodynamics, if these things are subject to random collisions, there will be a tendency for this gradient to slowly ease itself, relax itself until it sort of becomes uniform everywhere. The gradient disappears. That is called diffusion. And I think the most important thing to ponder here is that it is a purely random, undirected process. At any given place here, x naught, there will be a flux, which is number of flow particles per square centimeter, situated here. So if you have a unit area here, there will be particles passing by. That's called flux. And that flux here of particles is proportional to the derivative of this evaluated at this point here. In other words, this slope right here. The bigger the slope, the bigger the flux, faster the flux. Now perfume consists of uncharged particles. But if these happen to be charged, that flux would amount to a current, a measurable current. So there is Fick's law, which is in fact just this, which says that flux is equal to a coefficient, which is called the diffusion coefficient, multiplied by the slope of something, dy by dx. And this diffusion coefficient depends on the type of particle and the type of medium it's in, called the diffusivity or diffusion coefficient. Notice the minus sign. Is it clear to all of you why we have a minus sign there? Because the slope is negative, but the motion is in the positive x direction. If the diffusion process eliminates a gradient, there must be a minus sign. The gradient dies, must be minus. Another way of looking at it is, the gradient goes like this, negative, particles move in the positive direction. That's why we have a negative sign there. However, if we are talking about electric currents, if charged particles diffuse. They create a current, and all electric currents are by convention assumed to be positive. Even though electrons are doing the work, the convention of current predates the discovery of the electron, and we always say it's positive charge moving in a certain direction, which is the converse of the actual direction of electron flow. So if we have electrons like this, now I'll use n here, and we have a diffusion gradient here. Okay, we know the electrons are going to have a flux in this direction like so. And that flux will imply a current density, and I'll just give it in one dimension, which is given by, you'll have the diffusivity of the electrons, you will have the derivative of the density or concentration as a function of x, and then there has to be charge, because we're talking about current. But each electron carries a charge, q, and so that q will multiply this. Now let's figure out which way things, or what the sign of this should be. Remember that J is a vector, it's a current density, and the corresponding vector on the right side is this one right here. So in this case, if we have electrons moving in that direction, the conventional current is moving in that direction. Now, according to Fick's law, there's going to be a minus here because of the negative gradient, but then there's going to be another minus to get the J to be correct. So the two minuses cancel and ends up like this. On the other hand, if this was holes, which are positive things, then using the same argument, Fick's law says, so we'll call this Jn, Jp, Fick's law says that you have minus dp d sub p times the gradient. We add the electronic charge, the hole carries the same charge as the electron, except it's a positively charged particle. So if positively charged particles are moving in that direction, the conventional current is moving in that direction, which means the minus stays, because that relates to the fact that the slope here is negative. So you got that, the negative slope times this minus leads to a positive current. That's simple enough, just got to do with the two oppositely charged. Everybody follow so far? Now these are processes that are unique to p-n junctions. Now let's come to the p-n junction. This is really the cornerstone, as Dr. Sabi said, of all electronics. It has remarkable properties. It enables things that would be impossible in any other way. A p-n junction is a homogeneous crystal of semiconductor whose doping density changes rapidly or abruptly from p-type to n-type. So physically, it is this. This is a homogeneous semiconductor. That means it is an uninterrupted lattice. And at least ideally, you have a dividing line between p-type on one side and n-type on the other. How you make this is a marvel of modern material science. The important point is that whenever you have a transition here, you would expect some kind of disruption. Imagine if you take two pieces of material, one is p, one is n, and sort of glue them together or melt them together, you'd have a discontinuity at that junction. In modern p-n junctions, there is absolutely no discontinuity here. The crystal is absolutely 100% intact. That's essential for it to deliver what it is intended to do. So how it's made is a different story, but for now accept the fact that this is homogeneous. Now this is not complete because we can't do anything with it. In order to make it useful, we have to contact it so that we can drive something on the outside. So there are metallic contacts at the two ends. And those are discontinuities for sure. Because you melt metal into the semiconductor, it's highly disrupted, and silicon comes to an end. So it is a terminated lattice which is highly jagged because of the presence of the metal. We will now look at this in equilibrium. So we now can connect this to external circuits, external stimulus, and we look at it in equilibrium. Now before we do that, let's just see from what I have said so far. Supposing I create this pH junction at time t equal to 0, it comes into being. What do you think is a natural, spontaneous process that will take place even before I connect anything here? Can you see something there that might want to take place naturally, spontaneously? Yes?
Maybe electrons from the n-type would actually try to merge with the holes from the p-type.
Right. Why would they want to do that?
The opposite charge.
No.
So they drop down this.
No. Don't mutter, just raise your hands because I can't figure out. Yeah.
It's random process the electrons.
So,
So some of the electrons might pass through
what's the word that describes that process?
diffusion.
Very good. You see right away that there's a huge concentration gradient. Lots of holes here, very few holes here. Why is this very few and why are there very many? So, look at the concentration gradient. 0, infinite, 0. Infinite concentration, boom, huge diffusion current. Spontaneous, immediately. Of course, it goes the other way too. So electrons want to migrate over to here, holes want to migrate over here, electrons the other way, simply to level off the concentration gradient, driven by only the second law of thermodynamics. Now, if that were to happen without stop, then you just have a uniform P plus N material everywhere. Because everything would level off uniformly. So you have uniform levels, like two liquids of different colors all leveled out. But that's not what happens. Yeah?
Would there be a neutral barrier band in between when they start actually...
Well, hold on. I'm leading up to that. So do not anticipate. Just wait. So, if that were to happen, everything would level off. And if these were not charged particles, that's exactly what would happen. If they were uncharged things, that is exactly what would happen. Whatever density you have here would lower a little bit here and fill up everything. Whatever density you had lower here, fill up everything uniformly. That's exactly what would happen. What puts an end to it, or stops it midway, is the presence of charge. Because look what happens. If these holes move, they're not going to move from there. There'll be no motion of holes here. Why not? Why not? No muttering. Raise your hands. Yeah. Well, no. I'm going to select who. Yes.
Because it's the electron that will
No. Why is there going to be no motion here? It's all got to do with what I've already discussed. Yeah. There is no gradient. There is no gradient. It's what the gradient what drives things according to Fick's law. The gradient is only present right here at the junction. So only the holes here will want to move. Only the electrons here will want to move. Now when they move, this hole moves here, but the hole was due to, if this is p-type, due to a dopant. That dopant had one fewer proton and one less electron. So when the hole moves away, it leaves behind its parent dopant. Because remember, this is p-type, which means all the holes are due to dopants. We've already discussed that. So if this hole migrates over to there, it leaves behind its parent atom, which is stuck in the lattice, doesn't move. It has one less proton. In the context of things, one less proton, when you view it in the region, means a net negative charge, immobile. So, let's look at just one hole here. One mobile hole, I'll show it as a positive particle, mobile, moves out there. But this hole was due to a dopant which had one less proton, one less electron. That dopant impurity creates a local fixed negative charge right there, because its corresponding hole has left the region. So you have a shortage, you have an impurity that doesn't belong to silicon, which is one less. Similarly, if an electron moves from here to there, there's the mobile electron moved over there, it leaves behind its parent atom which had one extra proton, one extra electron, column 5. Silicon is column 4. That parent atom is jammed in the lattice, not going to move, but it does contribute a net negative charge because of one extra proton. When this electron is back here, on average there's electrons moving around here which neutralize this in a region, not locally but in a region, globally. But when this leaves the region, there's nothing to neutralize. One electron short in this region. Neutrality is violated, and so you see a net positive charge, immobile. Okay, well, when many of these leave, you end up with lots of exposed immobile impurities. Now here's what happens. You notice that this forms a dipole, separated layers of charge, like a capacitor. It's a dipole. And there is a net electric field that must run in this direction. Right? Uniform separation of charge. Does everyone see that? Because you only have positive charges here. Only. This is n-type doped. The dopants are one extra proton for each dopant atom, and those dopant atoms have lost their corresponding electrons over to that side. Similarly, one less proton, they've lost their corresponding holes to that side. So these parents are left behind. They all are close to the edge because that's where the concentration gradient is. And this forms a uniformly separated layer of two charges. Plus here because of the dopant atoms, minus there because of the dopant atoms. We've said that it's a p-n junction. Now this electric field is all uniform in one direction, and so let's say a hole comes along and wants to diffuse over here. As this field gets stronger, it will want to push that hole back because a positive charge will be pushed back. If an electron now, a further electron wants to diffuse here, it will see a negative charge over there, it will push it back. So as this dipole gets stronger, you have this retarding force due to an electric field. Diffusion is random. Electric field is a push. It's a forced phenomenon. It's a stimulus. So the stimulus builds up until it has enough of a barrier that it does not allow other diffusion to take place. That's the difference between charged diffusion and uncharged diffusion. So a dipole forms here, and clearly where these things are, there's very few electrons on this side, holes on this, because they're the ones that migrated, so you end up with this region here which is short of charge or depleted. And therefore the steady state condition so the equilibrium condition is this. That a dipole forms around the junction due to the impurity atoms or unneutralized impurity atoms And the electric field due to this retards further diffusion. So the picture is, I'll draw a graph now. This is the p-n junction, P and N. A region is formed here which may not necessarily be symmetric around the junction, with a set of positive charges here, immobile, set of negative charges there, immobile, it's called the depletion region because it is short of carriers, it has yielded its carriers. Immobile impurity atoms, dopant atoms. Let's say this concentration here of dopants was Na, this concentration here was Nd. We will also note that this p-n junction comes to an end and there's a metal contact here and there. There is an electric field that has been set up here. Now this p-n junction will come into equilibrium where that field is strong enough to retard further diffusion. The field doesn't exist without diffusion, but it's the field that stops it as well. So it's a self-limiting process. Everyone understand that? No diffusion, no dipole. No dipole, nothing stopping the diffusion. So diffusion takes place, dipole form stops further diffusion. Self-limiting. The p-n junction equilibrium is a beautiful illustration of the multiple laws and multiple conservation principles that must come into place for something to be truly in thermal equilibrium. There are numerous things that are going on here, and I will illustrate them one by one. You'll have to take notes quickly on that. First of all, whenever you have a dipole, you must terminate every positive charge with negative charge here. You cannot have unterminated, you cannot have more positive charges than negative, because if you did, that positive charge would seek out a negative charge somewhere to terminate its electric field on. So in steady state, there must be charge neutrality across the depletion region. Now supposing Na was 2 times larger than Nd, that is, you have twice as many dopants per cubic centimeter here than there. Right? Doping density is the average number of dopants per cubic centimeter. Let's say you have twice as many here as you do there. Can you see that as a result of this, the width of this depletion region on this side, if there are twice as many per cubic centimeter, will be 1/2 the width here because of this. Do you see that? So it determines the individual widths of the 2 sides of the depletion region. The second balance that comes into play is the Boltzmann equation. you must have recombination generation balance on each side away from the depletion region. The neutral region is defined as the area outside the depletion region. So you have two regions, either depletion or neutral. And here the recombination rate must balance with the generation rate, which we've already discussed. So if we label the neutral region, let's say we look at the p-type neutral region here, well, we have the number of holes in the neutral region, this is a level of holes, is given by the dopant density. The holes that arrive from the other side, the number of holes that go to the other side make a tiny difference to this. So we'll just say this remains at the doping density. Those holes are going to recombine with the electrons that are here. And we'll call those electrons NP0. N is electrons. They are sitting in a p-type material. And 0 means at equilibrium. Why are these two flat? If I'm drawing this along the direction here, why are these two flat?
Could you repeat that, because I couldn't see the diagram?
My question is, why are these two flat? If they weren't flat, there'd be a gradient, and therefore there'd be a current flowing. But when we talk about equilibrium, nothing is happening. It's just sitting there. There's no current flowing. The p-n junction is sitting on the table. Nothing is attached to it. It can't just have spontaneous current flow. So everything must be level. Now we have the presence of electrons and holes in each other's vicinity. In this area here, there's that many holes, there's that many electrons. They must satisfy this condition. Well, we know exactly what that condition is. In this area here, we must have Na times Np0 must be equal to Ni squared, because of our reasoning earlier. The generation rate is always the same. And let's say that the n-type region was less heavily doped. So this would be the doping density of the n-type, and we know from our logarithmic scale that you'll have more holes here. So we'll call this Pn0 from that picture back here. And so in this region, we must have Nd times Pn0 must be equal to Ni squared. Same Ni. So this is the second balancing act between recombination and generation in each side individually. Now here's the third balancing act. This is the stuff I've described so far is actually pretty simple. The third balancing act is the most subtle, but it's also the most beautiful. You have holes there. You have fewer holes here. This is a homogeneous material. Physics cannot tell the difference. As you move along here, it cannot tell the difference. But what physics sees is the following. You're in a region of a large number of holes. Then you enter a depletion region here, which has a dipole in it. It has an electric field in it. Electric field means that if a test particle was to move across here, it would have to do work against the field in the depletion region. So it would be at a different energy level here. Therefore, the holes that are there are at a different energy level than the holes that are here. And it's a homogeneous material. And it's in equilibrium, which does not in any way disallow Boltzmann's equation. In other words, if we were to ascribe a potential energy across this depletion region, the relative ratios of these two hole densities would obey Boltzmann statistics. Do you understand that? Similarly, the relative ratios of the two electrons densities would obey Boltzmann statistics. So in thermal equilibrium, since we can ascribe a potential energy to the electric field in the depletion region, and how do we do that? Well, since we're electrical engineers, or maybe some of you will be, or the majority will be, we would say that there's a voltage that develops across here. And if the electric field runs in that direction, the polarity of the voltage is this. Right? Every time you have an electric field, you have a potential difference. So the potential difference is measured by V, and we'll call it the built-in voltage, VBI. And therefore the energy in this field, U, is given by Q times VBI. That's the definition of voltage. Electronic charge times voltage is equal to energy. So therefore we would say that the ratio of Pn0 to Na is in fact equal to the ratio of Np0 to Nd. You see Np0 here and Nd there, Pn0 here and Na here. They're across, same particle but across a potential barrier. In both cases, this is proportional to the exponential of minus Q VBI over KT. And therefore it follows that we can directly, just by using the Boltzmann relationship, not only is it proportional, in fact it's equal. It's equal, and therefore just by invoking this law of probability we can deduce what VBI is. Thus, VBI is equal to KT over Q log of NA over NP0, or equivalently KT over Q, sorry, ND over NP0 log of NA over PN0. So we have an expression for the built-in voltage across there, just invoking probability, without doing any calculations of fields and integrating and so on. We don't have to use any electrostatics. So you understand how profound Boltzmann relationship is? Now, if we knew both of these things, we could calculate what that VBI is. Now we know this because that's under our control, but we don't know that, or we think we don't know it. We've already actually looked at some ideas here, right there. So if we do that, this whole thing becomes KT over Q log of NA and D over Ni squared. And now we know everything. We know what this doping is because we control it, we know what that doping is, and we know this is 1.5 times 10 to the 10. So we've calculated the built-in voltage. And for silicon, under typical doping conditions, since this is a log expression here, if you change that by a factor of 2 or 3, almost nothing changes in the end result. This VBI is on the order of something like 0.9 volts. So we say that there's a built-in potential barrier because of that dipole, and Boltzmann statistic is satisfied on either side of it. Okay, I don't want to stop here because this is where a lot of physics books would stop, but I want to take it one step further, and therefore I'm going to run over time. I want to now show you what electrical engineers would do with this. This is beautiful physics, but it's not enough. We want to use this in some way. So we've got these two wires coming out, and it's very tempting to start putting voltages externally across there. So here we have a PN junction. Couple of contacts, two wires coming out, P and N. I'm going to put a voltage source here. Apply a certain voltage V. Now if I apply, I'll start gently, start with 0 voltage and crank it up a little bit. Now you all know Kirchhoff's voltage law, even if you haven't studied it here, you know it from A levels or FSC. Apply a V here, that V must be balanced by a V across here. Now these regions here are neutral regions with lots of doping, lots of holes here, lots of electrons here. If you have lots of carriers, these are very low resistance. Lots of carriers, like metal has lots of carriers. This has lots of carriers, lots of carriers. This here has very few carriers because they all left, they've migrated. So it looks like this: a low resistor, then a depletion region of high resistance, then a low resistance here. That's what it looks like. Three things in series. Now if I apply a voltage across here, I think it's pretty obvious that most of this voltage will drop there, and hardly any will drop there. So all of this voltage, we say, drops across there. And VBI changes to VBI minus V. As in this direction that I've shown, it subtracts from VBI. Now VBI minus V means there's less potential energy across the barrier. If you shrink the potential energy across this barrier, if you shrink the energy barrier, diffusion kicks in. Remember, it's the barrier that held it back. Reduce the barrier, it starts again. But what's happening here is that in order to enforce this voltage, we have actually made a complete circuit. That P really wants to go over there. It really wants to go over there because of second law of thermodynamics. But there's something holding it back. Now I gently ease that retarding force. Well, this says, oh, fine. It starts diffusing. As it diffuses, it creates a current that flows in the outside circuit and continues to flow. In fact, it's a steady current. Electrons here want to diffuse over there. Reduce the barrier, they do start to diffuse. They flow into here, flow all around, and continue to flow. So a steady current appears, which consists of both an electron component and a hole component. Let's look at how those currents add up. If there is a net diffusion current of holes across here, let us say there's a hole current JP on this side. Strictly speaking, we start from the edge, but we're going to apply Kirchhoff's current law, which says that any current here must be the same current there, must be the same current there, must be the same current everywhere. So this JP is going to be the same as that JP, is going to be the same as that JP. This JN, which wants to diffuse over there, is the same as that JN, is the same as that JN. Now, do these currents cancel each other? Why not?
Both have negatives opposite of each other.
Right. So this corresponds to a conventional current in this direction. And since these are negatively charged, flow in that direction corresponds to conventional current in this direction. they reinforce. So that the total current seen coming out of here is equal to Jn plus Jp. Okay. Now all that remains is to find out how big this current is. So for that I'm going to draw a linear plot here, which is broken into two segments, linear scale, a break here of many orders of magnitude, continue with the linear scale here, all the way down to the end. Here are the two edges. Let's give it some dimensions. We'll call this WP, WN. There must still be some kind of depletion region here, but since we have applied a voltage, the net voltage across the depletion region has diminished to VBI minus V. I hope all of you can see this. VBI minus V. And it's in this direction. Since the barrier is lower, the Boltzmann statistics tell us that at least at the edge of the depletion region, if used to in equilibrium, if your concentration was this, that's my picture on that side, at least at this side of the barrier, since you've lowered the barrier, in steady state, this is not equilibrium anymore because we're applying an external agent of energy. But we are talking about steady state. Things have settled down. Things are happening continuously, not changing with time. This is a DC voltage. In steady state, since the barrier is lower, Boltzmann statistics says that the concentration gradient here must be, concentration here must be higher. Because concentration diminishes with the barrier, increasing barrier. Lower the barrier, concentration must go up. So since we have lowered the barrier by an amount V, the concentration here goes up from what used to be Pn0 to a new value, Pn0 exponential of QV over KT. V is the change. If this was 0, this quantity would be 0 and this quantity would be back to where it was. So the change in it is this amount by Boltzmann statistics. You see that? Because the barrier is smaller and it obeys exponential distributions. Meanwhile, at the edge here, since this is a highly disruptive lattice and we assume this is a long distance, that effect is not felt. And so here, for two different reasons, and I can't go into all the details, this remains steady at Pn0. So you have an elevated concentration here, the same concentration as before here, and you see there's a gradient here. Now that gradient is going to cause diffusion. So what will happen is you will have a diffusion of holes in this direction. But this is not in equilibrium, it's only in steady state. As these holes diffuse, they do not cause this concentration to go down, because there's a big supply of holes here. So as these diffuse out, more holes come here to top up this, because Boltzmann statistics must continue to be satisfied. So as these holes leave, more holes come across to top this up to maintain this at this level. So holes flow out, holes flow into there, and if you imagine that holes could flow in the wire, holes flow in here to compensate the ones that went from there, and so you see a continuous current. Now if we measure that current anywhere, we'll get the final answer. We can measure it here, we can measure it there, we can measure it there, Kirchhoff's current law. Current is continuous because you must conserve charge. Charge cannot accumulate. If it's moving out here, it must be moving in at the same rate here. So all we have to do is calculate the current at a convenient point, and I will do so here. So Jp by Fick's law is given by ignoring all the signs, I know the JP is running in this direction. It's given by Q times the diffusion coefficient of holes in silicon times the gradient here, which is Pn0 exponential of Q applied voltage over kT minus 1. That's the minus 1 gives the gradient divided by Wn. Can you see that? This minus that is this minus that. Simple triangle dividing by the base, Wn. That's the gradient. So that's the gradient. Of course, Pn0 must multiply it. Diffusion coefficient charge, that gives us the current. Exactly the same thing applies to electrons. Q dn, np0, I'll calculate on the other side, of course, e to the qv over kt minus 1. So when we add these two currents, so that means that therefore total current on the outside, so now we'll measure the current that is flowing through here. That current must, the conventional current must flow in this direction. I'll call it I. I've got to compute I from J, so I look at the area of cross section. So total external current I is equal to Jn plus Jp, because they both add, as we just discovered earlier, multiplied by the area of cross section. Well, if I look at these expressions here, I've got lots of stuff, but only one term which is common to both Jn and Jp depends on external voltage. So what I want to do is write a relationship between current and voltage. And I will take all these things here and lump them into, including the area of cross section, and lump them into a constant proportionality, Is. And then what remains is something that depends on voltage. It's e to the qv over kt minus 1. Okay, if you're lost a little bit at the end, we're about to reach the end, I will ask you what questions remain. So I'll answer questions then. Now let's look at this expression here. What I have here is a box which has two terminals. We're now making a macro model. I apply a voltage to it, and sure enough, a current flows. But it's not a resistor, because a resistor is characterized by a current voltage graph which is a straight line by Ohm's law. This is what a resistor would do. What I have is something that's given by that expression there. If V is positive, this exponential, notice how this works here. The expression is exponential of, I'll write it slightly differently, V divided by KT over Q. So clearly this must have the dimensions of voltage, because this must be, the power must be dimensionless. Well, this is a very well-known number to anyone who works in the area. At room temperature, this quantity only depends on physical constants, K, Boltzmann's constant, Q, and T. This quantity at room temperature is 25 millivolts. So if I apply a voltage, which is, let us say, 10 times this, I'll have e to the 10 here. E to the 10 is huge compared to 1. So you can forget about the 1. So if this exponential has a positive, reasonably large voltage, what you see is simply this exponential rising with V. And therefore, the characteristic will look like this, an exponential rise. So it starts off at a certain gentle slope and then rises exponentially like that. That's an exponential rise. On the other hand, if V is negative, I get an exponential of a negative number which gets very quickly close to 0, which leaves simply the minus 1 here. And so I'm just left with Is. So if you're plotting on a linear scale, whatever the value of Is, it turns out it's very small, but But whatever its value, if you plot on a linear scale, if the exponential grows positive, you get a huge increase. If the thing becomes constant with the same coefficient as the exponential, this must simply pin out to a constant value here, like that. You see that? Whatever this value, it multiplies the exponential. So if the exponential is positive, this gets magnified hundreds, thousands, tens of thousands of times. If it's negative, you simply see this value because of the -1. So on a linear scale, this will be tens of thousands times higher than this, always, independent of what IS is, just by the property of the exponential. So you have something that looks very nonlinear. Well, that's exactly what we want in electronics, because that's called a rectifier. And the rectifier has all kinds of properties, such as, just qualitatively, supposing I put into this rectifier a sine wave, which might represent, let's say, the AC voltage that comes out of that socket. Supposing I apply it on this axis here. I'm drawing the sine wave or time along this axis, voltage. The response of the rectifier would be this. When you get a positive voltage spike here, positive half cycle, this will give a big current. So you'll get a big current with a positive half cycle. Negative half cycle, you get almost no current. So what comes out is almost no current. Next half cycle is like that. Then no current. Now you may say, what's the point of that?
It's a unidirectional.
If you look at the average value of this voltage, the average of a sine wave is 0. If you look at the average value of this, and let's pretend it's also a voltage, the average value is non-zero. Now, in electrical engineering and also in physics, average values are often sort of roughly or slightly inaccurately called DC. This has 0 DC, this has non-zero DC. So every time you plug in that little thing into the socket which charges your cell phone and mobile computer, the computer takes 12 volts DC. The socket puts out 120 volts AC. How do you get from AC to DC? Through this. That's what the PN junction is all about. Okay, I'll stop there. Questions? I don't know how much time you will have to go over these concepts, maybe in your discussion sessions, but it's very important that you invest the time, if you've taken good notes, to really try to grasp the key concepts I've described. If you grasp those, you'll have mastered this at least to the introductory level, and it'll help you to build up. Nothing should here be a mystery. Everything should be explainable. So any questions remaining? Yeah? IS is just a constant of proportionality. Look at these numbers here. This, I lump them all together. That's IS. What remains is this factor here. Any other questions? Yes?
So the increase brought over there, not which you got that new expression exactly. Shouldn't it be utilized when we have more holes coming in?
These are holes.
But there was an increase initially, right?
Increase in holes. Those holes were supplied from this side. And now that increased value must be held in steady state, must be maintained because of Boltzmann statistics. Boltzmann says if you've got a smaller potential barrier here, then the relative levels of this and that should obey the exponential relationship. So since the exponential has now become smaller, this ratio has become such that that remains roughly constant because doping dependent. This must rise to satisfy the Boltzmann distribution. So it must be maintained there. That means if this flows out, others must come in. Steady state. Any other questions? Okay, we'll stop here then.